Okay, so this is where we left. And in the lecture today, well, in the first part of the lecture today, we're gonna go through the logic. Just a moment, let me try to exit the sharing first and then share it again. Okay, so this integrated example will include the estimation of the demand and supply functions, and we will also see how we're going to use the ISO utility functions to estimate the demand functions. So all these concepts we have already introduced in the previous lectures, but we want to use them to deal with the practical transporting problem. So let's start with the introduction about the problem, the example. Here we consider there are two towns. There's a town A and town B. And the population of town A is 14,000. And the town A is designed as the residential area, so most of the people live in that area. And town B is designed as the entertainment or the business area. There will be a lot, the people who live in town A will travel to town B for the activity, for different type of the daily activity. And there are two routes for them to drive from town A to town B. And one is the local road, which would be Route 1, is the local road. And the other one is the freeway, which is Route 2. And we are providing with some information about the town A and town B, and what's the activities in town B and what's the utility for these two towns. And with this information, we will ask you to determine the demand and supply functions. And now let's go through all the assumptions we have made for this example. First of all, for both routes, Route 1 and Route 2, they are governed by the green shared fundamental diagram of the for the traffic flow, which will show the flow density, speed density, or flow speed relationship. And this is the basic format of the green shared fundamental diagram. In this fundamental diagram, S, the speed is written as a linear function of the density. So here S is the average speed on the road, D is the density of the traffic, and dj here is the jam density, which is the maximum density on the road. Finally, we can use the product of speed and density to calculate the flow. So here, before I go to the further introduction about the background, I would like to give you some ideas about what the green shared fundamental diagram looks like. So basically, this is the flow density relationship for the green shared fundamental diagram. It's in a concave relationship. And the maximum value falls around the half of dj, the half of the jam density. And if we go to check the speed density relationship, it's in a linear decreasing line. So the highest one would be the road speed limit, and of course you can find out the speed will be 0 when it goes to the jam density. So this is about the green shared fundamental diagram. And well, both of them for Route 1 and Route 2, both of them follows the green shared fundamental diagram, but we have some specific parameters for Route 1 and Route 2. They are different. For Route 2, S2, which will be average speed on Route 2, is 60 times 1 minus D2 divided by 300. So 60 is the maximum or the speed limit, and 300 is the GM density. So this is for the route 1. And we also have some information about route 2. This is for route 2, and for route 1, we have S1 equal to 70 times 1 minus D1 divided by 175.33. So the speed limit is 70 and GM density is 175. And you can also find out the flow as the product of S1, D1. So that's the fundamental diagram with respect to these two routes. And this information is very important for you to determine what's the flow will be traveling from tongue A to tongue B. And also it's very important for us to determine the supply functions. And we also have more information. For the distance from A to B for both routes, for the route 1, route 2, the distance will be 5 miles. And also we see that we assume that the residents in tongue A can also take some activities inside tongue A. And if we are taking any activities in tongue A, well, which will be the internal activity, they will just take the local street in tongue A. And we assume that the average travel time in tongue A for any kind of activities is 3 minutes at any time, and without respect to the number of the activities in tongue A, it's constant value. And moreover, we provide the utility for the activity in each tongue, in tongue A and in tongue B. So for tongue A, we set the utility of XA as 10 times 1 minus exponential minus 0.1 times XA. So this is the utility for the activity in tongue A. And here XA is the daily number of the activity performed in tongue A. And the UAXA is the total utility in tongue A. And also we have a similar formula for the utility in tongue B. And UB will equal to 15 times 1 minus exponential minus 0.3 times XB. So this one shows the utility of the total utility in tongue B with the daily number of the activity XB. And clearly you can see that the factors, this factor will be much higher than UA, than the factor in UA, and which usually means that the utility at the tongue B is higher than tongue A. But if you consider the cost you need to take from your travel from A to B, then they will have limited number of the people who like to travel to tongue B. So this would be two typical utilities applies for the activities in tongue A and tongue B respectively. And now, in the first question, we have all the assumptions we made for this problem. And for the first question, we want to ask is like we want to find out an appropriate supply curve for the trip from A to B, and we also made the assumption that the travelers, it's for any people who want to drive from A to B, they will always take the shortest path, the shortest route with the smallest time. So this is the rational decision for any human driver. And so first of all, for the supply curve, well, from our previous definition, the supply curve will determine the price of the products as the function of the demand. In this case, that will be the travel time as the function of the volume. So this is what we need to derive for the first question. Find out the supply curve. And as we have already obtained the fundamental diagram for the two routes, route 1 and route 2, then we can determine the we can determine the supply curve based on the relationship between the travel time and the volume. So which will show how the travel time is determined by the volume. So for the for this kind of travel time and the volume relationship, it can be derived directly from the fundamental diagram. So let's first go to see the route 1, which would be the this kind of pink line. And we know, let's start from the fundamental diagram. In the fundamental diagram, S1 equal to 70 times 1 minus D1 divided by 175. And the volume is S1 times D1. So this is the green shaded fundamental diagram. Just the fundamental diagram. And then with the fundamental diagram, you can find out the speed as the function of the density and or as the function of the flow. So as the function of the flow. Let me use another symbol, G. And now you can then estimate the travel time as the function of the speed. Well, we know that the total distance, the distance of route 1 is 5 miles. So the travel time from A to B through the route 1 is the 5 miles divided by the speed. That's 5 divided by S1. So this is the relationship between the travel time and the flow if you replace S1 with the function of the V. So that is 5 divided by G1 V. So if we choose these ones. And well, we know the formulas of the S1 is the function of the D. We find out the relationship of the V as the speed and speed times the D1. So you can find out the formula of the G1. And with that, you can then get the relationship between the travel time and the volume. So this pink line just to show the relationship between the travel time and the volume of the first route. And similarly, you can find out the relationship for the I guess I'm putting the wrong. Sorry, I'm putting the wrong at the wrong location. So you can find out the relationship of the travel time with respect to the flow for the route 2, which would be pink line, and the blue line here is the it's for route 1. So they have very similar formulas, just the difference is about their parameters. And now we need, this is the connection with 2 routes. So if you still remember our previous lectures, if the two cities are connected with 2 routes, we will need to find out this their combined cost by not by adding their cost, not by adding the cost together. Instead, we need to find out what's the additional flow it can support. For example, if the travel time is less than 5 minutes, if we find the travel time is less than 5 minutes, which the 5 minutes is the smallest travel time for route 2. In that sense, no people will take route 2. Instead, they will only take route 1. So this is what is going to happen. This is what is going to happen when the travel time is less than 5 minutes. Everyone going to take the route 1. And then their relationship, the relationship between the travel time and the flow will be determined by the yellow part, the yellow line, the yellow dashed line in this figure. And if the travel time is higher than 5 minutes, which means that some of the vehicle will take Route 1, some of them will take Route 2. But the issue is like, for anyone who is taking Route 1, Route 2, their travel time will be the same. Well, this is based on the selfish of the human drivers. They will always take the best options for themselves. They don't think about what happens for the other users. With that, at the equilibrium point, all the travel time of all the routes will be the same. So this will give you the another case. If the travel time is higher than 5 minutes, then you can find out the total travel time, the total volume at that specific travel time would be the summation of the two volumes. For example, at the travel time of 7.4 minutes, from there would be 3,000 vehicles traveling on route 1, and 3,000 on route 1 and 3,900 on route 2. And this will give you the flow with respect to the travel time at 7.4 minutes. You can find out the other points with the similar strategy, and this is the part, the specific part where you will observe the below this region, below this line, all vehicles will just take route 1, and above this line, vehicles will take both route 1 and route 2. So that's the that's what we get about the relationship between the travel time and the volume. And this is just called the supply curve. Is what we want to find for this problem. And you can see that the supply curve is only determined by the fundamental diagram of the two routes. So that's the first question. And now for the second one, the second problem wants us to find out the Isotd curves for the demand for all the participations in activity at a location in town A and location in town B. So we have two different activities, XA as the activity in town A, XB as activity in town B. And we want to find out the Isotd curve, which means that the combined utility on each Isotd curve will be the same. And you will find out the relationship between Xi and Xb to show the Isotd curve. And so for the total utility, usually we have Uxa Xb will be the utility of at town A plus the utility at town B. And this happens when we assume that the utility are independent to each other, and this is also a common assumption. And now we have already provided with the utility function. We know that the utility of town A is 10 times 1 minus exponential minus 0.1 XA, and at town B is 15 times 1 minus exponential minus 0.3 XB. So that will be the two lines, blue for the utility at town A, pink for the utility in town B. To determine the utility function, we need to find out the combination of XA and XB to make sure that the utility of the XA and XB will be constant. So for example, if we start with the two points for the XA, for XA equal to 4, we get the utility of A for the town A is 3.3, and for xb equal to 2, we get the utility as 6.77. If we put them together, the total utility is 10. And if we go to search another pair of the xa and xb, for example, say that xa is 10, then you have utility as 6.32. You have xb equal to 1, then utility of town B is 3.89. And if we plus them together, it's also approximately be 10. And this indicates that the total utility for the first combination, xa equal to 4 and xb equal to 2, it's the same to the utility of another combination, xa equal to 10 and xb equal to 1. So these two should force in the these 2 points should force in the same utility curve, iso utility curve. And you can continue searching all different kind of the combinations, and eventually you can draw the iso utility curve. This is actually, you can also draw this line directly through this expression, UAXA plus UBXB. You know the expressions of XA, you know the expression of for the XB, and if we let them equal, let the total utility UXA XB equal to a set of values 5, 6, 7, 8, 9, 10, 11, 12, or any other values if you specified, then you can find out the relationship, derive this one as XA or XB equal to the function of XA. Then that will be the isotd curve. In your homework assignment, you probably need to carefully select the range of the utility. It could be between 5 and 12, it could be even larger or even smaller, depending on the parameters I assigned to each one of you. And with different total utilities, we can draw different curves, and those would be the isotd curves we can use to determine the optimal assignment for the activities in town A and town B. And that's what we get for the isotd curve. Actually, the resulting town A and town B will just be two preparations for the solution of the third one, which is the most critical one for you to determine the number of the trips that will travel from A to B, and how many of them will travel through Route 1 and how many will traveling through Route 2. In this problem, we assume that all the trips occurs during the period of 6 a.m. and 4 p.m. And the problem wants us to find out what's the hourly volume of the traffic on Route 1 and what's the hourly volume of the traffic on Route 2 for these two specific cases. And we also have the budget constraint. We see that for each trip, for each driver, the total travel time budget is 30 minutes, which means that for all the residents in this network, they will not spend more than 30 minutes to complete the all the activities, either in town A or town B. So there are some restrictions about the estimation of the flow. So this is basically what you are provided. Well, I believe that if you just start from here, it might be very confusing and you have no clue about how to solve it. But if you follow all the steps for the rest of this lecture, you will have a clear idea about how we're going to determine the demand function with this assumption, and how we're going to use the demand supply function and its equilibrium to find out what's the volume we should set for Route 1, Route 2. So let's start with the supply curve. In the supply curve, we determined that the travel time is a function of the flow, at town B, and the volume, the traffic volume, it's related to the activities that we take at time B. If we consider the whole period that is defined is from 6 a.m. to 4 p.m. So there will be 6 hours for the trip will occur in 6 hours. And we also know that the population is 14,000 in town A. That indicates that we can find out the number, the volume, the hourly volume based on the period, the daily trip it's going to take, and the total populations. So in this problem, we assume that the number of the activities that the each person will take in town B is XB. So this is what we want to identify. How many of the trips that each person will take in town B is XB. And in that sense, the total number of the trips we're going to take. So the total number of the trips we're going to take is definitely the population times the average number of trips that each person going to take. It's 14,000 times XB. And we also know that this trip, all these activities occurs in 6 hours. So we can find out the hourly volume would be the total divided by 6. So that is 14,000 times XB divided by 6. And if we do the calculation, that is 2,333 times XB. So this is the relationship between, I should put this one. This is a relationship between VB and XB. And of course, you have to know that the volume of the VB is the volume of route 1 plus the volume of route 2. Because this is in the parallel links, there will be 2 routes. And V1 plus V2 will be the total number of the flow from A to B. That is VB. And so this is the relationship we get. And if we have the average number of the trip as say that is 2.14, then you can actually calculate the the number of the volumes as 5,000 vehicle per hour, which would be which can comes from this equation. And you can then calculate the travel time as 6 minutes based on the supply curve. If we have the 5,000 trip, and then the travel time is 6 minutes, something like that. And then you can determine based on the fundamental diagram, you can determine how much flow you're gonna you're gonna be assigned for route 1 and route 2. But that's for the future steps. So for now, we just get the relationship between the flow from A to B, and the every daily activities in town B. That is XB. So with that, we can do another modification. By replacing the volume VB with XB. So the number of the daily trips for each person. And the way for you to get that is just simply scale the x-axis down by 2,333. So with that, you will get a new figure, and the one for the horizontal axis, that will be the daily trip in town B, and the vertical axis is still the travel time. So this is the slightly modification about supply curve. It's still in the preparation for this a simple preparation for this problem. Okay, and then we will go to examine the budget plan. So we know that the total travel time, the maximum budget, travel time budget, it's set as 30 minutes for each person, and we know that the travel time inside of town A is assume that it's a TTA, and the travel time in town B would be set as a TDB, which would be the travel time from A to B, either through Route 1 or Route 2. And TTA times XA plus TDB times XB should be less than 30 minutes. And in the previous assumption, we assume that a TTA is 3 minutes. So here we just don't know the 3 other variables, XA, TDB, and XB. In addition, we will try to remove this sign or as smaller than or equal to 30 minutes. We will try to utilize the insatiable assumption. In that sense, 3 times XA plus TDB times XB should equal to 30 minutes. It means that we will use all the 30 minutes budget. And here in this equation, TTB XB times XB is the value of the can be determined by the supply function, and it's what we have derived from the fundamental diagram. So the vertical axis is a TTB, and x-axis is a XB. So if we have this information, we can easily identify how to find out the optimal solution. So that's the budget constraint that we need to think about, and how the budget constraint is linked to the supply curve. And now we need to, as we have the budget constraint, we need to use the Isotd curve to find out the optimal assignment of the AAA and BBB based on different cost from A to travel time cost from A to B. So the figure here is the Isotd curve that we have already derived in the second problem, and for the budget constraint, as we showed previously, it just usually be in a straight line. But for this specific example, this specific problem, we know the price, the cost of the trip in town A, but we don't know the cost of the trip from A to B, because this one is related to, is also a function of XB. And this is a tricky part. We need to use the Isotd curve to also determine the function of XB, determine XB as a function of the travel time. And now let's see how we can determine that. Start from this Isotd curve. If you have the budget constraint, you will find out in the Isotd curve, which will be tangent to the budget line. And at the tangent point, you will have the optimal values for the 2 activities, XA optimal and XB optimal. And the slope and also the intercept to the y-axis will help you to determine what's the value of TTB. And in the next slides, I'm going to show you how to do this calculation. But as for now, you need to use as many Isotd curve as possible, and as many possible values, many possible values of the TTB to find out the tangent point to complete the estimation of the supply curve, which will be the curve of XB as a function of TTB. So for this specific problem, we have the budget constraint 3XA plus TTB times XB equal to 30 minutes. And clearly, if we know that XB, if XB equal to 0, then you can easily solve that XA is 10 And this is one point that the budget constraint must passing through. So back to the Isotd, to the figure of the Isotd curve, xb equal to 0, which indicates that the x-axis, and you can find out 1 point. So that's the where x-axis is. The all the budget line should intercept at this point. And now let's draw the first budget line. Let's draw one line. Let's draw one line which will be tangent. Draw the first line that will be tangent to the Isotd curve with u equal to 12. So that's the first one. And at this budget line, it will be tangent to this Isotd curve. And also it intercepts with the x-axis or the y-axis. Or you can draw multiple budget lines starting from the point at 10, 0, which would be the point that the budget line should pass, and tangent to all the other Isotd curves. So with that, you have 1, 2, 3, 4, 5, 6. You will have 6 lines, 6 points, 6 tangent points you can find. You can find out the 6 intercepts, and of course you cannot. But for this case, you cannot find out the tangent point to the utility equal to 5 and 6. This is they are too small for you to determine. Now you have all these tangent points and intercepts. We can then, using this information, to determine what's the demand curve for this problem. So for assuming that for all the intercepts, it will be xb1, xb2, xb until get to n. Say that there will be n budget lines you draw from the from this origin point and tangent to the Isotd curve. And also you can find out what's the expression for each one of them. Basically, you know the value here, you know the value of the intercept. You also know another origin point. Then you can determine what's the slope of the line, and that slope will be helpful for you to determine what's the value of the TTB. And in addition, we can also find out the in this specific program, we know the values. We know all these values. There will be 5 or 6 points, and or we know the we also can find out the joint point or the tangent. We also can find out the tangent point, which would be the optimal point for optimal assignment for XA and XB for each budget constraint. And with that, we can then quickly solve the value of, or find out the value of TTB with this equation 30 divided by XB, which would be the at the point XA equal to 0, which would be all these intercepts. So quickly find out the value of TTB, and then we know the value of the travel time from A to B for each budget line. So for the first one, that is 6.38 minutes. Second one is 6.69 minutes. And for the last one, you get it's 20 minutes. This is the value for the value of the travel time for each budget line. And you can also find out the optimal assignment of XA and XB for each budget line. For this, we put them together and let them put all of them in one in one table and draw all these lines together. If we draw all these lines together, it will help you to form the demand curve. But it's not this curve, it's not this red line. This red line just connect them together is the points we need to think about. If we put them together, we can then find out the actual relationship between the demand, between the activity, and the travel time cost from A to B. So we have the budget line. In this table, we have the budget line, and it shows the intercept at x equal to b, and you use this equation to calculate what's the value of the travel time from A to B. That is TDB equal to 30 divided by XB. And at the optimal assignment, you have the number of the activities at A and B. For utility equal to 20, you find out the value, the travel time from A to B as 6.38 minutes, and the utility that you get is that you're gonna get is 3.6 minutes, the 3.6 trip per day, and you can find out the values for the other utility lines that you have already draw the budget line to get the tangent point. And then let's just pick up these two columns. Pick up these two columns. You can then draw the relationship between the travel time and the number of the trips in the demand function in the figure with the demand functions. And from the previous study, we found out the supply function, which is determined by the fundamental diagram. In the previous table, we found out the demand function, which is the demand for the activity in town B. And these two functions, these two lines, will actually intercept with each other. And this kind of intersection is the equilibrium point between the supply and demand, and that's exactly the point we want to find. If we go to check this point, the travel time here is 7.4 minutes, and the flow here is 2.96. So that's the solution we're gonna get. For all the assumptions we have made, for any people who want to travel from A to B, from town A to town B, the travel time is 7.4 minutes, and the volume or the average number of the activities they're going to take for each person is 2.96. So that's the two values we get. And now we need to use this information to determine what's the volume we're going to what's the hourly volume in route 1 and route 2. The analysis is pretty simple and straightforward. So first of all, we can determine what's the total volume from A to B, and then we're going to convert them to the hourly volume. We have already determined that XB equal to VB divided by 2,333. So it's relatively easy for you to find out what the value of VB. That is 69,000 vehicle per hour. And for the trip B, the number of the total number of the time they're gonna take is 2.96 times 7.4 minutes. That's the total time they're gonna the total time they're going to spend for this activity. And for the activity in tongue A, well, what you get is you have XA, TTA, here equal to 30 minutes, and you have XA, TTA equal to 3 minutes, TTB equal to 7.4 minutes, and XB equal to 2.96. So you can easily find out what's the value of the XA. In this case, you find out XA equal to 2.7 trips. So for each person, they're going to take 2.7 trips in tongue A and 2.96 trips in tongue B. So that's the equilibrium point for this problem. And we still have the problem about how many, what's the volumes in route 1 and route 2. So to do that, that will be pretty simple. We will go back to the supply function, especially for the original supply function about the travel time with respect to the volume for route 1 and route 2 independently. And we find that the travel time from A to B is 7.4 minutes. So if we start from the travel time of 7.4 minutes and draw the horizontal line, you're going to intercept with the relationship for route 1 and route 2. And in route 1, if you can go using the curve to track the volume, you can find out the volume is 3,000 vehicle per hour. In route 2, you find out them as 3,900 vehicle per hour, and that's what's the volume we're gonna observe for tongue A and from route 1 and route 2. And of course, you can find out what's the hourly volume for the traffic in tongue A itself, but that's only determined by the value of XA. So with that, I think I finished the example. And I would like to reserve several minutes for the question before the break. Do you have any questions about this analysis?
Yes, Professor.
Yes. Go ahead. Yeah.
So, Professor, for this analysis, like, did you do this in? Can we do this in Excel or MATLAB, or we have to do by hand?
I would recommend you to do everything with some program languages or Excel. Excel would be very it still be complicated. The most tricky part is about this one. How to identify the tangent point to all the isotd curve. You need to find out the value of the intercept for each budget line to the y-axis, and also find out the tangent points for each isotd curve. And for your homework assignment, if you choose this, for some settings, if you choose this region, you may only find out like 2 or 3 isotd curve where you can get the tangent point. With that, you should find out the smaller utility values or larger utility values depending on the situation you have, to get a more tangent points and more candidate budget lines. I would recommend to get at least 6 points for you to achieve more accurate result.
Okay, thank you.
Any other questions about this one? So this is actually a combined combined example, tell you how you're gonna consider the fundamental diagram. The fundamental diagram is applied for you to determine the supply curve for in transport system. And they will also tell you how to use the Isotd curve. And the Isotd curve here is applied for you to search the demand function, demand curve. And once you have supply and demand curves, you need to combine them together. The joint, the intersection as the solution you need for the similar problems.
Excuse me, Professor.
Yes.
Are these examples going to be on the today quiz?
No, it's not. This is too complicated. It's just for the whole homework assignment 2. It's about the same problem. I'll just give you different parameters for you to solve.
Yes, thank you.
Okay. Okay. I hope that I did not miss any questions in the meeting chat. If anyone has the questions in the chat, just let me know. Okay. So with that, we will take a break, and we're gonna take a break for about 10 minutes, and resume the meeting at 4:10, and we're gonna start the introduction about the Emerson tutorial. Okay. With that, I will turn off my camera, mute myself, and if you have any questions, feel free to leave the questions in the meeting chat.
Thank you.
Okay, I guess it's time for us to resume the lecture today. And to start this Amazon tutorial, I'm going to change to my other computer, but I will keep this computer on to record the video. And with that, you will have a chance to go through all the fundamental skills later after class. And also, I would recommend you to, if you have already installed the Student Edition, I would recommend to open the Student Edition and follow the steps I made during the lecture and do some practice. I will also give you some chance to give you some time to do the practice by yourself in the lecture. So with that, let me try to change my computer. Okay, I need to turn off my video here, camera here. Okay, can you hear my voice? Is there any interruption?
No.
Great, yeah.
Okay, that's good. That's good. So, let me share my screen first. So I've at first given a very brief introduction about what is Amazon. And basically for the lecture today, we're just gonna cover some fundamental skills. Most of them comes from the tutorials from Amazon's manual, and I will just pick up the part that I believe is helpful. It's most important, most fundamental for you to build a network and start to run by yourself. So first of all, what is Amazon? Probably let me start with the website introduction. So if you go to Amazon.com, you can find out their website, and I believe this is a part for you to download the. I share you the link, and you can find out the student editions. You can find out the student editions, and the whole it's free for all the students. It's the expert edition. So this is the most powerful. Is the most powerful license. The expert edition is the most powerful version. And, but of course, for the student edition, there will be some limitations about the size. Originally, I know that there are some issues about for you to save the network, but you still have any issue about this. Abdul, will you mind to mute yourself? Yeah, thank you. So I hope you all have already signed up at this website and get the license, at least student edition. And we're gonna do all the tutorials in this not in this edition, in the similar platform. For my side, I have the full license, so it might be a little bit different, but the fundamental skills I'm going to introduce will be the same. So first of all, Amazon from their website define themselves as the multi-resolution, multi-model modeling tool. So it's already designed for the traffic simulations to simulate how vehicle is moving on the road, and it's capable of conducting the simulations at all the three layers: the microscopic level, the mesoscopic, and the macroscopic. At the microscopic level, they will be able to model the behaviors of each individual road users, the vehicles, trucks, pedestrians, and they are also considering loading the models for the cyclist. And for the mesoscopy level, they will consider the flow instead of the individual vehicle behaviors. So they will have the link level average flow modeled over the time, and also they provide some microscopy level models, but it's not the advantage of the Amazon simulator. Amazon is more about the microscopy and mesoscopic. And this platform is very useful and very flexible for you to do different modelings, especially city level modelings. And it offers some features, the embedded features for you to develop the advanced vehicle technologies, connected vehicles, the CACC control, autonomous vehicles, and so on. But those would be some fundamental tools. And they are also provide the API for you to conduct some development of the advanced or the real-time advanced traffic management systems, so that it can model what the future city looks like. And if you are working on the connected and autonomous vehicles, you can develop whatever functions or the applications through the API to manage the behaviors and the infrastructures in their platform for the large-scale city. And of course, they have different editions, the professional editions, advanced editions, and the expert editions. And with different editions, they will have different add-on packages, and they have different limitations about the scale of the network. For the student edition, it's an expert edition, so it's very powerful. It contains most of the functions there. But it may have some limitations about the size because it's only applied for the educational purpose. So there, for the tutorial today, we're gonna cover some fundamental network editing skills, including how to create a network, what's the component in the network, how will you modify the features of those components, and how can we set up the simulation runs, including setting the traffic demand, apply the traffic signal control plan, and also if you want to model a large network with different path assignment, it will give you a method to find out the path assignment efficiently. So this would be the contents I'm going to cover today. I hope I can finish all of them today, but depending on how easy for you to manage these all these skills. So with that, so the way for me to deliver this tutorial is like I'm gonna try to develop some network through the Amazon platform, and also you can try to follow the steps that I'm working on to build the network by yourself. So first of all, definitely let's start with the first step for us to build a network is start from the scratch. And let me show you how to do it. So first of all, we need to open the Amazon Next 20. That's the latest version we have for now. Now, once it's open, you can decide. You will have several options to develop your own. You will have several options to develop your own project. I think my phone here is a little bit small. Let me try to see how to adjust it. It's weird. Everything here is correct, but it's so small. Hopefully you can see this this button here. It's called a new project, or if you cannot see it, it's fine. Just go to the file and select a new. This will give you an option to develop a new project. I have no idea why it's so small. Well, let me exit the presenting first and go back again to see whether it's able to improve the quality of the interface. It's still the same issue. Let me just quickly check it. That's pretty weird for on my side. I need to think about whether to make it better. Just a moment. Give me several minutes to adjust my computer. I never see such problem previously. I will probably restart my computer and see what's going on there. Just give me 2 minutes to restart my computer. In the meanwhile, I hope you can initiate or open your own Amazon software on your own computer, and I'm going to show you how to develop the models, new network, and then give you some chance to practice how to create a network in Hamilton or some place around the McMaster University. CM7. Okay, back to the normal. Okay, so can you see my screen now?
Yes.
Yes.
Okay. I hope the phone is acceptable at this time. Okay. So the Once you open Emerson, it will jump you to the a blank page about developing new project. So we can work on a new project. And a new project, you can decide we're gonna store your file. So for example, I'm gonna store my file under the this course, and now I just placed it here. And you need to define the project name. So this Emerson tutorial 1. And definitely need to use the Emerson template, or you can use the other type of the template. The other type of template, the most common one is the Emerson template.